Okay, now we have some increasing and decreasing questions. Ignore the numbering here with these. This is just the next one on. So find the intervals which the derivative is positive and negative. Well, what do you know? When the derivative is greater than 0, the function is increasing. When the derivative is less than 0, we're decreasing. And you know the increasing is going up, decreasing is going down. So you see right about here, it switches. Right about here, it switches. And obviously here at the asymptote. So for this interval right here, the graph is going down, 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 down. So that's where my derivative is negative. Then here it goes up, so my derivative is positive. Then it's going down, derivative is negative. And then here, derivative is positive. So as far as the intervals go, we look at the x values here, here, and here. And this interval is from negative infinity all the way up, because you know this will keep going, going, going. So negative infinity all the way up to an x value of 0. That's where it's decreasing. Then from 0 up to, this is a 2, it's increasing. Then from 2 to, it looks like 4.5, we're decreasing. And then 4.5, and it keeps going to infinity. So 4.5 to infinity, we're increasing again. Okay, so it's about connecting derivatives and what the shape of the graph does to see whether the derivative is positive or negative. Okay, so this question's somewhat similar on the problem is they didn't give us the graph, so we got to find these things computationally. So first thing I want to do is find the derivative. So the derivative would be 3x squared minus 27. So then what we want to do is figure out when does the derivative equal 0 and when does the derivative not exist, because that's the critical values, and the critical values will help us find the increasing and decreasing. Well, this is a polynomial, so we don't have to worry about not existing. But equal to 0, yes, this could happen. So move the 27, divide by 3, I get x squared equals 9, so x equals plus and minus 3. There's two x values where the derivative equals 0. That's where we set up this plus minus chart. So we got negative 3, we got positive 3. We're looking at the derivative and figuring out where the derivative is positive and negative. So I'll plug in negative 4, 0, and 4 into the derivative. So square 4, 16 times 3 is bigger than 27, so it'll be positive. 0 would give me negative, 4 would give me a positive. So that tells me my function is increasing, decreasing, increasing. This chart is not your answer. You have to write f of x is increasing on the interval from negative infinity to negative 3 and 3 to infinity. F of x is decreasing on the interval from negative 3 to 3. So this is what I'm looking for. You use the chart to get your answer. All right, here, same deal, same directions, increasing, decreasing. The problem with this one is the derivative is a little bit harder. So I'm going to leave it as is, and I'm going to do the chain rule. So my derivative will be the derivative of the, or sorry, not chain rule, I'll do quotient rule. So derivative of the numerator is 1 times t plus 3 squared, minus derivative of the denominator times t, so that would be 2 t plus 3 to the first, all over t plus 3 squared would give me to the fourth. So what I'm going to see here is they're simplifying. This thing could get really messy, but I'm going to find an easy way. T plus 3, t plus 3, t plus 3. So what I'm going to do is I'm going to factor that t plus 3 out. And so what I'm left with is there's still going to be a t plus 3 here because it's squared, minus t times, this t plus 3 is gone because it's to the first power, so times 2, all over, this will now be t plus 3 to the fourth, but when I cancel it with this one, it'll be now to the third. So I end up with the derivative to be, this is minus 2t, and t will be minus t, so I get 3 minus t over t plus 3 cubed. All right, so critical numbers. When is the derivative 0? When does the derivative not exist? All right, well, being that this is a fraction, when the numerator equals 0, that's when it'll equal 0, and when the denominator equals 0, that's when it's not going to exist. So this will be when t equals 3, and this will be when t equals negative 3. Make my chart, negative 3 plus 3. We're looking at what's happening with the derivative, not the original function, so I'm plugging things into the derivative. We'll go negative 4, 0, and 4 again. So when I plug them in here for t, negative 4 in for t, that becomes positive 4, so that's 7, so it's a positive in the numerator. When I plug it into the denominator here, this is not negative, so just ignore this. When I plug it into the denominator, that's also negative cubed, so I get negative is still, so I get positive over negative, so that'll be negative. Plug in 0, I get a positive. Plug in 0, I get a positive, so I get positive. Plug in 4, I'm going to get a negative over a positive, so then that's negative. So what does that tell me? Decreasing, increasing, decreasing. Again, write it. F of t is decreasing from negative infinity to negative 3 and from 3 to infinity. F of t is increasing from negative 3 to 3. Here we need to determine the critical numbers for the function and then find the relative max and mins based off of those critical numbers. In order to do that, first thing we need to do is find the derivative. So if you look at this derivative, this should be very easy. Being a polynomial, you get 12x cubed minus 24x squared plus 12x. In order to find the critical numbers, we need to figure out when is that derivative going to equal 0, when does that derivative not exist. Being a polynomial, we don't worry about not existing. So now it's just where does 12x cubed minus 24x squared plus 12x equal 0? Well, being a polynomial equation, this should be really easy. I'm going to factor out a 12x, which is going to give me x squared minus 2x plus 1, which you see will give me 12x times x minus 1 squared. That tells me x has to equal 0 or x has to equal 1. So those are your two critical numbers. Once you have those critical numbers, what we're going to do is place those critical numbers on our number line. And we're going to determine where the function is increasing and decreasing by looking at the first derivative. And then when we determine that it's increasing and decreasing, that could help us find our relative max and mins. So we're going to plug a value in here. We'll say negative 1. Here will be a half. And here will be 2. We'll plug this into the derivative. And we're trying to figure out whether or not we have a positive or negative value for that derivative. Negative 1 plugged in. Here, this would be negative 1 times 12 will be negative 12. Plugged in here, we're going to get positive 1, so we have minus 24. And plugged in here, we're going to have a minus 12. Well, you see, this is all negative, so that's definitely going to be a negative right there. Then we're going to plug in a half. Cube a half, you're going to get an eighth. Minus square a half, you're going to get a fourth. Then 12 times a half. So if you look at what happens here, this would give me, if I simplify this fraction right here, I would get, what, 3 halves. So that's 3 halves minus 24 divided by 4 would be 6, plus 12 divided by 2 would be 6. So the minus 6 plus 6 cancel, I get 3 halves. 3 halves is positive, so that's a positive right there. Then I'll plug in 2. 2 in here, 2 in here, 2 in here, and I end up getting what, 12 times 8 minus 24 times 4 plus 12 times 2. So you see that what we're going to get here is 12 times 8 is going to give me this 96, minus 24 times 4 would give me 96, plus 12 times 2 would give me 24. So these cancel, and you see you end up getting another positive. Okay. So what do we have? We have our function is decreasing, then increasing some more. So out of all these different values, 0 and 1, the only one that could possibly be a max or min would be 0. I say possibly a max or a min because that's where the function switches from plus to minus, or increasing to decreasing, or decreasing to increasing. In this case, we're decreasing then increasing. But the next question is, does 0 give you a point on the original function? Is it in the domain of the original function? And the answer is yes, because that's a polynomial. Okay, so the question said, determine the critical numbers. We did that. Then classify each critical number as a relative max, min, or neither. Well, this critical number, x of 0, is a relative min. And this is neither. Now that's just the x value. If you actually wanted to find the point, we would need the y value as well. We all know that in order to get the y value for a point, we go back to the original function. So the point would be 0, f of 0. That would be the actual point where the relative min exists. But this question just said to tell me whether or not that critical point is a relative max or min. Okay, so for this function, it says determine where the second derivative of the function is positive or negative. Now, second derivative has to do with concavity. Concave down versus concave up. Concave down, the second derivative is negative. Concave up, the second derivative is positive. So, if you look at this, follow this as we go left to right. We're starting here. We're curving on a downward trend. So from there to there, our second derivative would be negative. Then, right here, it starts to switch. And now my graph is turning upward till I get to right about here. Then my graph starts to change again. And I start turning on a downward trend. I'm going up, but I'm turning down all the way till about here. And then right about there, the graph starts turning back up again all the rest of the way. So if you look at the x values here for which this happens, we have these intervals split up. So on this interval here, we have our negative. On this interval here, positive. On this interval here, we're turning down, so negative. And on this interval here, we're positive. So to answer the question, f double prime is negative on negative infinity all the way up to here, which would be negative 5. And in here, which would be, it looks like negative 3 to 0. Now, f double prime is positive on this interval and this interval, which goes all the way down. And so this interval is from negative 5 to negative 3. And this interval goes from 0 all the way up to positive infinity. So here we have to determine where the graph of the given function is concave up and concave down and find the coordinates of all inflection points. So doing this, we're going to find the derivative. It should be 3x squared plus 12x plus 1. Then we're going to find the second derivative, which will be 6x plus 12. Then we need to determine whether or not the second derivative is 0 or the second derivative does not exist. Well, being that this is a polynomial, we don't have to worry about does not exist. So in order to figure out where the second derivative is 0, it's pretty simple. 6x plus 12 has to equal 0. You see that x would have to be negative 2. So that's pretty simple. So we have negative 2, our single value where we're looking at the second derivative. So I'll take negative 3 and let's say 0. And I'll plug them into this second derivative. Clearly right away you see when you plug negative 3 in, you get a negative. When you plug in 0, you get a positive. So that tells us we're concave down and we're concave up. So let's say f of x is concave down on the interval from negative infinity to negative 2, and f of x is concave up on negative 2 to infinity. The other thing is we want to find the coordinates for the inflection point. Well, since the concavity changes here at negative 2, this could be an inflection point as long as I can plug negative 2 into the original function and get a y value so I can get a point. And you see clearly that's going to happen. So the inflection point, and the only inflection point, is negative 2 comma f of negative 2. You don't actually have to sit here and find f of negative 2. You could. You plug negative 2 in here, here, and here, calculate it. It wouldn't be that bad. But for right now, it's not really necessary. Just tell me how you would find it. You plug it in. That's how you get the y value. All right, so here we want to use the second derivative test to find the relative max and mins. We can use the first derivative test, which is the whole increasing and decreasing concept, which you saw in a previous example. But now we're going to use the second derivative test to do the same thing. First thing we need to do is find the second derivative. So the first derivative would be 4x cubed minus 64x. The second derivative would be 12x squared minus 64. Okay, so now we know that relative max and mins come from critical values out of the first derivative. So that's what I'm going to do first. I'm going to say let's find the first derivative 0 and the first derivative not existing. Same example over and over again. This is a polynomial. We don't have to worry about not existing. So when is 4x cubed minus 64x equal to 0? Well, I'll pull out a 4x, and I'm left with x squared minus 16. So I see I get x equals 0 and x equals plus and minus 4. So there are 3 critical numbers. Then what I'm going to do is I'm going to take those 3 critical numbers and I'm going to plug them into the second derivative. So I'm going to find f double prime of 0, f double prime of negative 4, and f double prime of positive 4. And what I get out of this will tell me whether or not each of these values will result in a max or a min. So plug 0 into the second derivative. I'm going to get 12 minus 64, which ultimately gives me a negative value. I'm going to plug negative 4 into the second derivative, which will give me 12 times 16 minus 64. That's going to give me a positive value. Then I'm going to plug positive 4 in, which will also give me 12 times 16 minus 64, which will give me a positive value. So that tells me that this x value is sitting on a concave down picture. If it's sitting on a concave down picture, then the point has to be a max. The opposite's happening here. Concave up, min, min. So I could say that 0 comma f of 0 is a maxima, and negative 4 comma f of negative 4 and 4 comma f of 4 are mins by the second derivative test. All right, on this question, we want to basically put everything together. So, a couple of things here. We're going to find the first derivative. That would end up being 3x squared minus 6x. I'm going to find when the first derivative equals 0 or does not exist. Again, does not exist is not an option for this polynomial, so 3x squared minus 6x equals 0. Factor out a 3x, I get x minus 2. So I get when x equals 0 and x equals 2. So I have 2 critical numbers from the first derivative. I'm going to plot those. I'm going to look at the first derivative. Negative 1, 1, 3. Plug those into the first derivative. Plug -1 into the first derivative, what you see is you're going to get a positive. Plug +1 into the first derivative, what you see is you're going to get a negative. Plug 3 into the first derivative, again, what you see is that you're going to get a positive. So what we end up with is that our function is increasing, decreasing, increasing. Okay. We also know that this point right here, since 0 can get plugged into the original function, would be a max. And this point right here, since 2 can get plugged into the original function, would be a min. So we know that f of x is increasing from -infinity to 0 and from 2 to infinity, decreasing from 0 to 2, has a max at 0, so let's find f of 0. F of 0 would be 0. And let's find f of 2, which would be 2 cubed minus 3 times 2 squared. So you end up getting 8 minus 12, so -4. So has a, what do you say, max at 0, 0, and a min at 2, -4. All right, so that's a lot of information right there. All just came out of the first derivative. Then we're going to look at the second derivative. So let's section this off. We're going to look at the second derivative. Second derivative is going to be 6x minus 6. That's going to equal 0 when 6x minus 6 equals 0, so when x equals 1. It doesn't, and you don't have to worry about not existing, again, because polynomial. So then I'm going to do my table for this one. I only have this one value of 1. I'm going to look at the second derivative. I'm going to plug in 0 and 2 into here. You plug 0 in for x, you're going to get a negative. Plug 2 in, you're going to get a positive. So that tells us concave down, concave up. So we could say f of x is concave down on -infinity to 0 and concave up on, 0, 1. This value right here is 1. And 1 to infinity. And f of 1 is going to be 1 minus 3, so -2. And we can say there's a point of inflection at 1, -2. All right, now I'll start putting this together here. So what do we got? Well, we have a couple of points here. We got 0, 0. We have 2, -4. And we have 1, -2. -2 is -4. So these are a couple of points that we know our graph goes through. What do we know? That we are increasing, okay, and concave down over this entire interval right here. We hit a maximum. We are still concave down, but we switch to decreasing till we hit here. Now, from that point on, okay, we switch to concave up, but we're decreasing for a little bit longer. So we're concave up, but we're decreasing. So what we're turning, our graph is turning up. Then, from this point, we switch to increasing, but we're still concave up. And so my graph's going to look like this. So concave up here, concave down here, maximum, minimum, increasing and decreasing all holds. That's what your graph's basically going to look like. Okay, our recreation department plans to build a rectangular playground having an area of 16,900 square meters and surrounded by a fence. How can this be done? So we use the least amount of fencing. So simple rectangle. The area is 16,900.
we want to know the perimeter essentially. Well, you know, area of a rectangle is length times width, and we know that that's going to be 16,900. So we have length, we have width. The perimeter is 2 length times 2 width, or plus 2 width, sorry. So we have these two different equations, in which case the thing that we're trying to use is use the least amount of fencing. If we're using the least amount of fencing, that's the perimeter, that's our primary. That makes this our secondary. So what we can do is we can take this equation right here and solve for either L or W pretty simply. Let's just say we solve for L. So L equals 16,900 divided by W. And I can take that L and I can plug it in here for L. So now I have that the perimeter is 2 times 16,900 over W plus 2W, which I can also write as 2 times 16,900, which would be what? 33.8. W to the negative 1 plus 2W. Okay. Then we could take the derivative of P. If we take the derivative of P, we're going to get negative 33,800 W to the negative 2 plus 2. If I'm trying to find the least amount of fencing, I'm trying to find a minimum. This is the derivative, so now I need to find the critical numbers from this derivative. Well, I have to rewrite this. Negative 33,800 over W squared plus 2. I could also write that as negative 33,800 plus 2W squared, or 2W squared over W squared. Write it all as one fraction. Now, what I'm going to do is find my critical numbers. Well, when is this thing going to equal 0? When does this thing not exist? Well, the derivative would equal 0 when the numerator equals 0, which is negative 33,800 plus 2W squared equals 0. And it's going to not exist when W squared equals 0. But when W squared equals 0, W equals 0. Well, how could your width equal 0 for your rectangle? That would make no sense, so we're going to ignore that. So over here, what we could say is, all right, well, W squared, if I move the 33 and divide by the 2, well, you're going to say W squared equals 16,900. So W equals plus or minus the square root of that, which would be what, 4,300? No, that's divided by 2. That's not right. So the square root would be 130. So the negative doesn't make any sense because how could a W be negative, just like how could W be 0, so ignore that. So we really just have W equals 130, okay, positive. Well, as long as that ends up being the minimum, then we're good. So how can we determine if it's a minimum? We could do a couple of things. One, we could do the second derivative test, which I like the best. So I'm going to take the second derivative of P, which if this was the first derivative, do it again, you're going to get positive 2 times 33,800 W to the negative 3 plus derivative 2 would be 0, so you get this. If you plug a positive in here, remember this is a negative exponent, but that's really going to give me a positive value in the denominator times this, and so you see you're going to end up getting a positive when you plug 130 in. Well, if I got a positive in the second derivative, that tells me I'm concave up. Concave up tells me that I have a minimum for this value. So we know that that's your minimum. W of 130 is your minimum. Well, now we just need to figure out the length. Well, here's an equation that tells us how to find the length. So if you take 16,900 divided by 130, you get 130 again. So in terms of meters was the measurement. So meters, that's your dimensions. And once you have those dimensions, that'll give you the least amount of fencing possible. So if this thing is more square than rectangle, okay, 130 by 130 meters, that will use the least amount of fencing. Still giving you the 16,900 as your area, but least amount of fencing. Okay, so this one's a little harder. Store selling a popular computer game at a price of $44 per unit. And at this price, the players have been buying about 72 units per month. The owner of the store wants to raise the price so that for each dollar increase in price, he knows that he's going to have 3 fewer units sold each month. So each unit costs the store 26 bucks. What price should the game be sold to maximize the profit? All right, so you have your basic profit equation. Okay, your basic profit equation is that profit equals number of units sold times the profit per unit. Sorry, this is sloppy. Profit per unit. Okay? All right, so let's look at the number of units sold first. So we know that in looking at sort of the number of these units here, we know that we did 72 units per month, right? But remember, that's going to decrease because he knows he's going to have 3 fewer units every dollar he increases. So it's not going to be 72 units every month. Every time they increase it, it's going to go down by 3. So we start off with 72. Then we're going to subtract off of that. Okay, so we know it's going to be 3 fewer for every dollar increase. So there's going to be 3 less per increase. Well, increase over the 44, right? But we don't know how much we're going to increase it. That's the thing. We want to figure out what price we should work with. So if we take the price that we're going to think about selling it for minus what we originally were selling it for, that whole thing will tell us the number of units sold. So for every time we go up by a dollar, we get 3 less. So we have 72. Let's say we don't go up by any dollars, right? Let's say we don't go up by any dollars. We can figure out what it would be. And so the new price would be 44 because it was already 44. 44 minus 44 would be 0. 0 times 3 would be 0. 72 minus 0 would be 72. That's exactly how much we would have if we didn't go up at all. But if we go up by $1, so now we're at $45 or $46 or $47, we'll subtract off that many 3's off of the 72. So that's our number of units sold. Then we got to go to profit per unit. Okay, so we know that it's going to cost $26 to make a shirt. And so if we sell it for 44 and we take off the 26 of cost, we have our profit per shirt. If we're not selling it for 44, we're going to increase every time by $1. Remember, X was the amount that we're going to sell by, the amount of money we're going to use to sell each shirt. And subtract it off of 44, and this will be the increase, right? But X itself represented the amount of money we want to sell the shirts for. Well, if we know the amount of money we want to sell the shirts for, sorry, I keep saying shirts here. We're talking about computer games. So if we have X is the amount of money we want to sell this computer game for, and the cost to make the computer game stays fixed at $26, then X minus 26 would be our profit. Okay, the selling price minus the cost should give you your profit per unit. So this right here is our total profit equation. Now, if we're going to try and maximize this, we're going to have to take the derivative of this. This is not going to be easy to do right now, but what I'm going to do here is rewrite this a little bit. So for here, I'm going to say I can factor a 3 out of this, in which case I end up with 24 minus X minus 44 times X minus 26. So then I have 3 times 24 minus X will be minus X, and the minus 44 gives me a plus 44 when I distribute this in. So 44 and 24 gives me 68 minus x times x minus 26. That's much easier to then take the derivative of. So now I'm going to take the derivative of this profit equation. 3 is a constant multiple. This is a product, so I'm going to do the product rule. Derivative of the first is negative 1 times x minus 26 plus 68 minus x times the derivative of x minus 26 is 1. So what I end up with is 3 times negative x plus 26, distribute that in, and then this is going to be plus 68 minus x. So what do I get? I get 3 times negative 2x plus 94. So what you see here is you end up with this derivative. Now, in order to find maximums or minimums, we need to figure out what the critical numbers are. Well, when is that going to be equal to 0? Well, that'll be equal to 0. This derivative will be equal to 0 when minus 2x plus 94 equals 0, which will happen when x equals 94 over 2, which would be what, 47? Okay. So 47 is x. Now, that's our critical number. If that in fact ends up being a maximum, then we got everything we need. If that's not, then we're not going to be able to answer this question. Well, how do we figure if that's a maximum? Again, I like second derivative tests, so I'm going to find the second derivative. This being the derivative, the 3 is a constant multiple. Take the derivative, I get negative 2. So negative 6. So no matter what I plug into the second derivative is always negative 6, which means it's negative. Negative means concave down. Concave down means any critical point would be a maximum. We only have one critical point, so there's your max. So the idea is, what's the price that we should sell the game for to make a maximum profit? X, remember, was the price that we're going to sell for. So $47 would be that exact price to maximize the profit. If you go over $47, while you might make money, you're not going to make it at the same clip you were before because you're selling less units. So 47 is right around the perfect, is not right around, it is the perfect selling price so that you can maximize your profit. Right? You can increase your cost, you can increase your price of your item and say, I'm going to sell this computer game for $1,000. And if one person buys it, then great, I made a bunch of money. But one person might not buy it, or you might only get one person to buy it. Where if you sell them at $47 a piece, you're still going to have a lot of people buying your product. 72 units per month. It's going to be less than that, but you're going to have enough people buying your product that your profit will be at its maximum.
All right, here's your test number 3 review for Calc for Business. First thing we're going to do is differentiate a couple functions. So in this case, we're going to differentiate a function that has an exponential in it. Being that it has an exponential in it, you have to remember your derivatives of exponential functions. But that's not the only thing going on here. This is also a product. So what we're going to be using is the product rule. So when I take the derivative, I have two parts here. I have the x and I have the e to the negative x cubed. So you should remember your product rule. I'll take the derivative of the x, which is 1, times the e to the negative x cubed, plus I'm going to take the derivative of the e to the negative x cubed times the x. Well, e to the negative x cubed, you rewrite the exponential, then you multiply by the derivative of the exponent. So that would be a negative 3x squared. So this is multiplied by this e. So other than that, there's not a whole lot we can do here. A couple of ways we could write the answer. I could write this as e to the negative x cubed minus 3x cubed e to the negative x cubed. That's this times this. That's where I get the negative 3x cubed. I could write it like that. I can see that they both have an e to the negative x cubed in them. I could factor that out. 1 minus 3x cubed. If you want, this has a negative exponent. If you want to write it so it doesn't, we could also write it as 1 minus 3x cubed over e to the positive x cubed. Any one of these would be acceptable answers on the test. I really don't care which one you would give me, but this is not the final answer. So 1, 2, or 3. Either one of those would be fine. Here's another one, in which case you want to find the derivative of y with respect to x, t, or theta. Well, in this case, since we have x's, we're going to take the derivative with respect to x. And so the idea, though, is this is a logarithm. So in order to take the derivative of the logarithm, we use our u prime over u rule. But I don't want to take the derivative of this whole thing. It'd be kind of messy. So what I'm going to do first is I'm going to use some of my log rules to rewrite the function. So y could equal log of 1 minus x minus 5 times the log of x plus 4. So that's taking the division and turning it into subtraction, and then this power coming out to the front of that term with a multiple. Now I'm going to take the derivative. So I have this log minus this log, so I can do each one separately. U prime over u. Here's my u, so the derivative of this, which would be negative 1 over that. Minus 5 times, same deal again, derivative of this divided by this. So that'd be 1 over x plus 4. So I could write my answer as negative 1 over 1 minus x minus 5 over x plus 4. For a test, that would be fine. There's not really much else we can do there. To simplify it, although lots of times you'll see it written as a single fraction, which would be 1 minus x times x plus 4, being the common denominator. So this will be negative 1 times x plus 4 minus 5 times 1 minus x, ultimately giving me what this will be positive 5x, this will be a minus 1x, so that'll give me a 4x. This will be a negative 4, and this will be a negative 5, so it'll give me a negative 9 over 1 minus x times x plus 4. So oftentimes you'll see that given as the final answer, but for the test, I think that would be just fine. All right, so we have some integration now. In this case, we're just doing indefinite integrals or antiderivatives. So polynomial, this should be one of the easier ones you do. In which case, if we're doing the integral of this polynomial, since they're added together, you can do each one separately. The constant multiple 7 and the 8, they can come out. So in which case, I'm going to get 7x to the 4th over 4 plus 8x squared over 2 plus 7x plus c. And if you're not sure that that's the correct answer, take the derivative of this and you should get back to here. Here's another example, a little bit more difficult. What I'm going to do is rewrite this one first before I do an antiderivative. As is, it's going to be very difficult. So what I'm going to write first is everything in exponent form. So this will be x times x to the 1/2 plus x to the 1/2 over x squared dx. Then these two come together to give me x to the 3/2 plus x to the 1/2 over x squared dx. Then what I'm going to do is split this apart into two separate fractions. Okay, I'm going to write this as x to the 3/2 over x squared plus x to the 1/2 over x squared, all dx. Then I'm going to simplify each one of these fractions. So I'm going to subtract the exponents, in which case I'm going to have an x to the minus 1/2, and this one's going to be x to the minus 3/2 dx. Now that I have it in this form, this is the easiest form of this function to integrate. Now I just integrate each one separately using power rule. So sometimes you have to manipulate your function before you integrate it. So what I end up with is going to be x to the 1/2 divided by 1/2 would be multiplied by 2 plus x to the minus 1/2 divided by minus 1/2 would be multiplied by a minus 2 plus c. So I'll clean this up a little bit. 2x to the 1/2 minus 2 over x to the 1/2 plus c. And that's going to be your answer. You can change these x to the 1/2 as into roots, so I could say square root instead of the 1/2 power, but I really don't care which way you write it, root or exponent. All right, here's one we're going to have to do more by substitution than anything. We can't really rewrite the function in any other way that's going to be helpful for us, but we can do some substitution, in which case I'm going to say that u equals 7x squared plus 3. The derivative of that would be 14x dx. Now notice, if this comes out to be u, that'll be u to the 5th. What's left over is this x dx, but I don't have this to be x dx. I have 14x dx. So I can easily move this 14 over to the other side by dividing, in which case this integral will become the integral of u to the fifth over, under du over 14. Now I could put the over 14 here, but I'm going to put it out because over 14 is a constant multiple. So now if I go to integrate this, I have 1 over 14 integral. I'm going to write this as u to the negative 5 du, so now I can use the power rule. And now it's really easy to do. So in which case I get 1 over 14 times u to the negative 4 divided by negative 4 plus c. Well, 14 times negative 4 equals, we got 1 over negative 56 times u, which was 7x squared plus 3 to the negative 4 plus c. If you want to go one step further, I can write this as 1 over negative 56 times 7x squared plus 3 to the fourth, all in the denominator, plus c. Being that this is a negative exponent, I really should bring it all to the denominator, and there's your answer. Here's one where we can do another substitution. Usually when you see logs inside your integral, it automatically tells you want u to be the logarithm. So this is log of x to the sixth. I want that to be my u. Because differentiating a log is something we really haven't done. Integrating a logarithm is something that we haven't done. We've differentiated logarithms. So we're going to take the derivative of the logarithm, in which case what I'm going to do here is I'm going to bring this power out to the front first. So it's going to be 6 log x. And so my derivative is going to be 6 times 1 over x dx. Now if you look, if this comes out as my u, what's left? I have a dx over x. Well, 1 over x dx is dx over x. So I have everything here except for this 6. Similar to the last problem, I'll divide by the 6. So what do I end up with here? Dx over x is du over 6. So the over 6 I'll put out here. And then this was u, and so that's sitting in the denominator as my u. And so now what I have is the integral of du over u. Well, if you remember, that is the derivative of a logarithm, right? We took the derivative of the logarithm, we did 1 over u, dx over x, du over u. It's all the same stuff. So this will be log of u plus c. So then I get 1/6 log of log x to the sixth plus c. Here's a similar one, same idea. I want u to be my logarithm. I could write that as 4 log x, so that when I go to take the derivative, I have 4 times 1 over x dx. Again, 1 over x dx is dx over x. I have a dx over x. That's the u I just used. So this one turns into u du over 4, because this 4 is going to divide. And so I'm going to get 1/4 u squared over 2 plus c. Well, the 1/4 and the 1/2 is going to give me 1/8. U was log of x to the fourth squared plus c. Yeah, let's look at this one. Another substitution. You got to recognize these as substitution because you see a function and that function's derivative inside the integral. So if I let u equal 2 plus 3x cubed, the derivative is going to be 9x squared. Now I got a 10x squared instead of a 9x squared. But we can make that work. So this 10 is a constant multiple that I can pull out, and this 9 is a constant multiple that I can divide. So if you look at this, if I pull the 10 out, I have x squared times the fourth root of 2 plus 3x squared dx. So if this is my u, x squared dx is going to be my du over 9, and this 10 is just sitting there, so I get 10 over 9 fourth root of u du. Now fourth root is 1/4 power, So I'll write that as u to the 1/4 power du. And then I could just use power rule. So I get 10 over 9 u to the 5/4 divided by 5/4. Well, divided by a fraction. We've done this a bunch of times. You're going to flip and multiply. Plus c. So I'm going to have 4/5 times 10/9 times u, which was 2 plus 3x cubed to the 5/4 plus c. Now what I can do here is I can cancel this 5 and this 10. I'm left with a 2. So ultimately I end up with 8 over 9, 2 plus 3x cubed to the 5/4 plus c. All right, so this one, now we're getting into the definite integrals. So this one says find the total area of the region between the curve and the x-axis for y equals x squared plus 1, where x is between 0 and 1. So if you were to sketch this out real quick, you could get a really easy graph done here. X squared plus 1 is a parabola up 1 unit. Everyone should be able to handle that pretty well. Here's x of 0, here's x of 1, so it's bounded by the x-axis. Up here, up here. So this is the area we're trying to find. So we talked about these are the rectangles here. But rather than adding up those areas of rectangles, we talked about how this area can be found by doing the integral from 0 to 1 of x squared plus 1 dx. By taking this function, which is this y equals x squared plus 1, bounded by the x-axis between this interval and this interval, that area can be computed using this definite integral. Now, as far as the definite integral goes, the idea is first we need to find the antiderivative of this. That's pretty easy. It's going to be x cubed over 3 plus x. Remember, no plus c needed here. Then we're going to evaluate it between 0 and 1. So I plug 1 in, which will give me 1/3 plus 1, minus I'm going to plug in 0, which will give me 0 over 3 plus 0. So that's just 0. So 1/3 plus 1 is 4/3. So that area right there is 4/3. Okay, in this question, they weren't asking you to find the area. They're just asking you to do the definite integral, in which case we're going to use some substitution to get this done. I could multiply this out and do it as a polynomial, but it's actually easier if I say u equals x plus 2. Du is the derivative, which is just 1 dx. And so I can turn this into the integral of u cubed du. Now the trick with substitution is that this is 0 to 3. So the idea here is these are x values. We just switched over to u's, so we got to be careful there. So what I'm going to do is I'm going to find the antiderivative, which will be u to the 4th over 4. We're still between 0 and 3. Remember, no plus c is necessary. I'm going to resubstitute in my x plus 2. Now that I'm back to x, and remember, these were x values from the start, now I can plug them in. So I'm going to say 3 plus 2 to the 4th over 4 minus 0 plus 2 to the 4th over 4. And so what I end up with is, what's this, 5 to the 4th, which would be 625 over 4 minus 2 to the 4th, which would be 16 over 4. So I get, what's that going to be? That's going to be 609 over 4. Okay, here's another definite integral. Again, we're going to have to get this one done by some manipulation. In this case, not substitution though. I'm going to treat this one similar to one we had earlier with the x to the 1/2, where we split it up. So I have 1 over 4. I'm going to write this as t squared over square root of t, which already is t to the 1/2, plus 1 over square root of t, t to the 1/2, dt. The idea is I split this over this and this over this. Okay. Now the reason I did that is because now I can simplify this fraction. If I simplify that fraction, that'll give me t to the 3/2. And if I bring this up, it'll give me t to the minus 1/2 dt. So now I'm going to integrate, in which case I'm going to get t to the 5/2 divided by 5/2 means multiplied by 2/5. Then I'm going to have t to the 1/2 divided by that would be times 2. between 1 and 4. Now, we never did substitution here, so from the start, these two were t values, and we're still having t values, so now I can just plug it right in. So I'm going to get 2/5 times 4 to the 5/2 plus 2 times 4 to the 1/2 minus 2/5 times 1 to the 5/2 plus 2 times 1 to the 1/2. Now 1 to any power is 1, so that's easy. Now this one should be pretty easy too. 5/2 is 5th power second root. Well, second root of 4, if I do the second root of 4, I'm going to get 2. Then 2 to the 5th is going to give me 32. So I have 2/5 times 32 plus, I'm going to do that again here, but this is just the square root of 4, which is 2 times 2, so that's going to be 4. This will be minus 2/5 plus 2. Right? Actually, sorry, that's wrong. This whole thing is being subtracted. So that negative has to distribute in there and there, so this actually is a minus 2. So what I end up with here is this will be 64/5 minus 2/5 will give me 62/5. 4 minus 2 will give me 2. So that's going to be 62/5 plus what, 10/5. So that gives me 72/5. All right, so here, this one's probably the easiest one of the bunch, in which case we got to do this definite integral, but it's just a polynomial. So this should be really easy to find the antiderivative. If we look at this thing, we could just go right at it. We can say 8t plus t squared plus t cubed between 5 and 7. Plug in 7. I'm going to have 8 times 7 plus 7 squared plus 7 cubed minus plug in 5. 8 times 5 minus 5 squared minus 5 cubed. Now the hardest part of this whole thing is probably just doing the arithmetic part. So the 8 times 7 will give you the 56, plus 7 squared is 49, plus 7 cubed is 343, minus 8 times 5 is 40, minus 5 squared is 25, minus 5 cubed is 125. So if we do that computation there, what do we end up with? So it's 56 plus 49 is 105 plus another 343 gives me 448 minus 40 minus 25 minus 125 ultimately gives me what's that? I'm getting 258 out of that. So I mean, again, that's probably the hardest part of this whole thing. The integration should have been real easy.